Good morning, IB. This is 13B, where we're looking at lines in 2D and 3D. So far we've talked about the vectors as just a directional vector, transformation vector, and we don't, whether it's here or there, it hasn't made any difference. These are the same directional vector, which is quite correct. What we're now doing is we want to now define a line. So here's a line down here, and we want to describe that. Might be the movement of a boat or a plane or a car or whatever it might be. So if we know we've got a point on this line and we know what direction it's going, then we can define the path that it's travelling in. So we need a direction vector and a point. So remember, our points have usually been something like, let's just go our point A by this direction vector here. That's going to be A1, A2. And we could also write that, because that has a coordinate point. If we're talking, we could be 2 or 3D, but we've got, in this case I'm just doing two-dimensional. It's our coordinate or direction from the origin. The direction vector it's going to here is defined as B in our diagram. So that means whether we do the wiggle or an arrow, doesn't matter. B1, B2 are our X and Y directions for our direction vector, or it'll be B1, B2, B3 when we get to three-dimensional. So to find any other point on this line, all we need to do is get, so in other words, our point R, OR is the direction vector for our point. We need a starting point, in this case A, and then move from A to R. Now we know that AR is parallel to B, all right, so we know our direction vector is B, then it's going to be some multiple of B to get from A to R. Before we've written that as a K, so we've done like K times our direction vector. In this case we're using a T. It doesn't matter, the K or the T is just a parameter. So when we come up with our equation, then we can say any point R, given by that vector R, can be found by knowing a starting point plus T lots, the parameter, times our direction vector. So in here, A is a point on the line, or our starting point. Starting point. So our parameter is our T, our direction vector is B. If we remember our opening problem that we looked at in 13A, we had our yacht sailing and it started off at our point 617, which is up here, plotted on the axis. Where are we? At 1 o'clock it's at 617, at 2 o'clock it's now at 1014, sorry, it started at 220. So here we've got several points on our line. We've got a direction vector, so we can calculate any position it is later, assuming it continues with that same direction vector from, and it doesn't matter which point we take, it just determines how many direction vectors we're going to look at. So our starting point we could take as any of those, this initial one or the one at 1 o'clock. So let's take 220 where it started. So our initial vector, our starting position, oh, was that A? Yep, that was A, was 220. And our direction vector was, if we saw each time we went 4 in the positive direction of the X and -3 in the Y. So our direction vector was 4 and -3 in the Y. So now we can write our vector equation to find out any point OR. So OR, so we could write that as R1, R2, that R will equal our starting point, 220, plus T lots of our direction vector. Now we're going to do more looking at velocity in that later. We're going to see that this T is going to represent our time because this is our velocity. But we'll come and look at that in more detail later, and we also looked a little bit at that in the first section. So, in general, a vector equation for any point R, so if we've got our point OR, we could write that as little r. We could use R1, R2, but we could also write it as XY because they're our coordinates in our two-dimensional space. Will equal our starting point, A1, A2, plus T, B1, B2. So that's what we've seen. Or we can abbreviate it right down to go, R is going to equal our position vector of some point on the line plus our parameter times the direction vector. So the thing to remember, this is our direction vector, this is a parameter. Our parameter that we have here, in this case, we've used a T, but we could use an S. You'll find you use different consonants for those parameters. We can now split these into parametric equations, in other words, an equation involving involving the parameters. So we can split that and write it x is equal to A1 plus T lots of B1. That's called a parametric equation because we've broken it down for each of the components using our parameter. That can be rearranged, and we'll look at that in a moment. There's the y version, A2 plus T lots of B2. We can also, just wait. Right, sorry about that. Just wanted to add this Cartesian form. We can come up with our Cartesian form of the equation by equating our T values. So here we've got our parametric form. So we can make T the subject by going x minus A1 all divided by B1. And down here we can make T is equal to y minus A2 divided by B2. So when we try to come up with our Cartesian form, like the normal form that we would use for an xy plane, we can equate these two T values and come out with x minus A1 over B1 is equal to y minus A2 over B2. We can rearrange that and we'll have our equation in x and y because these are just numbers. We'll do an example for that in a moment to make it look a bit easier. So in two-dimensional, we've got lines that are lying in the plane, in our xy plane. We can come up with our vector equation, which is what this is, in which case we've got a point on the line, that's this point here, and our direction vector here. So this is the point, this is our direction vector, and that's our parameter. Each parameter, every time you change T, you get a different point on the line. So one point is made from one T value. We can also use the direction vector to determine the gradient of the line and vice versa. We've seen this before, where we talked about that in chapter 12. So if our direction vector is B1, B2, that means our point is moving, I'm just going to go this direction in this case, B1 in the x direction and B2 in the y direction. whatever they might be. So remember, your gradient is rise over run. So that means our gradient must be B2 divided by B1. So in our example with our boat, when we were going a direction vector of 4 minus 3, that means the gradient of that line was minus 3, the rise, which is the y value, over the run, which is the x value. So it's a negative slope, and that made sense from our diagram back here, a negative slope of 3/4. So if I know the gradient is 0.5, then that means I can rewrite that as a half, write it as a fraction. So this is like the rise, that's like the run. So that means I can write our direction vector, which is, call it B. Our direction vector could be 2, 1. But I could have just as easily written 3, 6. Which means our direction vector would have, well, it's not going to be exactly the same. Our direction vector could be 6 over 3. Or I could have written that as minus 1 over minus 2, in which case I would have had minus 2 minus 1. They're all the same direction, different magnitudes. So if this was something moving, I'd have different parameters, because this is like going, if that was a speed, that's going faster than this one. They're all going the same direction and the same ratio. If I wanted a line perpendicular to our example here, remember lines that are perpendicular times -1 over the reciprocal, okay, gives us 1. So in other words, if I want to take the negative reciprocal of that, if a gradient's got a half, then the line perpendicular to it will be negative, take the reciprocal, 2 over 1, which means I can write my direction vector as 1 minus 2. So this was 2, 1. So what have we got to do? We're swapping these. Swap your x, oh, that's a. Swap the x and y. Right, that's what you're doing when you're taking the reciprocal. 2, 1 becomes 1, 2, and make one of them negative. So I could have just as easily written that as 2 over minus 1, which means I would have had minus 1, 2. Both of those are the same. They've got the same gradient, same direction. Okay? If we're into 3-dimensional, all we do is have that extra component here. We still have our general point x, y, z to find a point R on the line. We have our starting point, A1, A2, A3, and our direction vector B1, B2, B3 times our parameter. Again, each point on the line is defined by one t value. When you're talking about gradient in 3D, we can't just go rise over run, because it's from what perspective. So certainly any line in space has got a slope on it, but it's not as easy to define in 3 dimensions. It's got different perspectives. So you can't just easily work it out. Let's just write that perspective. In terms of parametric equations, then we can break that all down. So we can go x is equal to a1 plus t lots of b1. Y is equal to a2 plus t lots of b2. Z equals a3 plus t lots of b3. So remember, if we want to make a Cartesian form, we equate the t values, which means rearrange each of the parametric equations to make t the subject, and then equate them. So we'll end up with an equation with 3 parts because we've got 3 components here. So let's look at some examples of these. We want to, for each of these, come up with a vector equation, the parametric and the Cartesian. So here we can see we're all working in 2 dimensions. Let's do a couple now, and then we can do a few in class. So for A, all right, we've got our direction vector, and it goes through this point. So our vector equation R, this is part 1, R will equal our point, which is 3, 4, 3 minus 4 at least, plus our parameter times direction vector. That one's easy. The parametric equations will be x equal to 3 plus, so we just work our way along the top, 1 times t, so I'm just going to go 1 t, which is t, 3 plus t. Our y parametric equation is going to be minus 4 plus t lots of 4, so it'll be plus 4t. To get our Cartesian equation, remember we want to make our t the subject in each of these. So in the first one, we've got t is equal to x minus 3. In the second one, we're going to have, need a bit more space, t is equal to y plus 4, all divided by coefficient of t, which is 4. We can now equate these 2 t's, that's a t, believe it or not. We can equate the 2 t's, put those together, so we can now see that y plus 4 over 4 equals x minus 3. Multiply both sides by 4, we get y plus 4 equals 4x minus 12. Y is equal to 4x minus 16. So we've come up with our normal x linear equation, y equals mx plus b, but coming about it from a different perspective. This one here, the next one, if we've got a line passing through 5, 2, there's our point, but if it's perpendicular to 5, 2, a line's passing through that and is perpendicular to this. So it happens to have taken the same values for the point and the direction vector. So to get our perpendicular line, do you remember what we did? We swapped the x and y. So it's now going, instead of 5 in the x, it's now going 5 in the y. Instead of 2 in the y, it's going 2 in the x. And make one of them negative. So your call, you can make, I'm making minus for the negative, for the 2. You could have put minus 5 and left the 2 positive. It doesn't matter. I'll put that other option. Okay, so you could have had 2 and then minus 5. Next one here, I've put on new page. If it's parallel to this vector here, it means it's got the same direction, and it cuts the x-axis at minus 6. If we're working the I and j notation, then you need to come up with your equation in that notation. So for C, we've got, for part 1, our vector equation, R will equal a point. Now if it cuts the x-axis at minus 6, it means its coordinates must be minus 6, 0, if it's an x-intercept. So we have minus 6i, because that's the x component, 0j, because it's the y component, plus t lots of If it's parallel to that, then we can just take it exactly the same. 3i plus 7j. So that's the vector equation. The parametric, we can break it down into the parts and then pull that all out to make a Cartesian. A line passing through these 2 points, the first part you're going to need to do here is to find the gradient between them. So your gradient, remember, is your y2 minus y1. So we'll go 12 minus 11. I'm taking that as x1, y1, x2, y2, divided by minus 3 minus 1. What's your negatives? So we get 1 over minus 3 plus 1 makes minus 2. So therefore our direction vector is going to be rise over run. So that's your y and that's your x. There's our direction vector. If we're going to write those equations, you would just normally choose one of them, and it doesn't matter which one. So we can go, our xy for our point is going to be, let's take the first one, minus 1, 11, plus t lots of minus 2, 1. The other equation is xy, and we could take the other point, minus 3, 12. If I was writing them both in the same sort of story, I would need to take a different parameter here. So let's take s with minus 2, 1, the same direction vector, but because we're starting a different point, we'll need to take different amounts of this direction vector to get the same point over here, to reach that same point. And we'll see that more and more where we want to take different values. If we're working in 3 dimensions, then it's just you're coming up with your vector equation, your parametric, so we're not worrying about the Cartesian one here. Again, in the IJK notation. So have a go at that and then come to class and we'll do that together in class, see what you come up with. This one here, find the parametric equations for the line through these 2 points. Then that's the story again we talked about. If you're using different equations, different starting points, use different parameters. So hopefully that's given you a good start on what to do with coming up with lines in both 2 and 3 dimensions. Thanks for listening. Have a good day.